In Lesson 4, we'll discuss near number arithmetic, that is, addition, subtraction, multiplication, and division of near numbers, along with their so-called indeterminate forms for limits, which we'll prefer to call star forms. These arithmetical operations each take two arguments, and they operate much as functions do, one pair of slices at a time on all of the numbers in those slices. This lesson is split across 3 videos. This first video will discuss addition and subtraction. The next will discuss multiplication and division, and the third video will review the arithmetical star forms as well as those for powers, including the way in which they're all connected. Part 1 of our discussion of near number arithmetic will focus on the operations of addition and subtraction. Before starting, a remark is in order. Formally, subtraction is defined as addition of a negative. We don't always think of subtraction in this way, but in the context of near numbers, we'll find it advantageous to do so, because addition is easier to think about, and we've already said all that we have to say about negation during our video on functions and near numbers. Let's start with nothing. We were all taught that when we add 0 to 0, we get 0 as their sum. Don't worry, the rules of arithmetic for numbers are just fine, and calculus doesn't change them at all. We're just going to broaden our horizons and see how arithmetic works with near numbers. Let's start with the sum of 0 plus and 0 plus. It's fairly clear from the start that since both summands squeeze closer and closer to 0, their sum should also squeeze closer and closer to 0. Moreover, all numbers contained in the slice of these two near numbers are positive, so all of the sums of those numbers will also be positive. Thus, we'd guess that the result should be 0 plus, and we'd be correct. Now let's see that all happen. Here we have slices of the two summands. What we need to do is plot all sums between a number in the first summand and one in the second. We'll get a whole set of numbers. To help figure out what that set is, we'll start by looking for its extremes. How small and how large can a sum of one number from each slice be? We'll get smaller sums from smaller summands, such as 0.1 plus 0.1 equals 0.2, and 0.01 plus 0.01 equals 0.02, etc., giving us arbitrarily small positive sums. We'll get larger sums from larger summands, such as 0.4 plus 0.4 is 0.8, and 0.49 plus 0.49 equals 0.98, giving us sums arbitrarily close to, but less than, 1. We'll also get all the numbers in between. The set of all sums from these slices gives us the open interval from 0 to 1. A quick note, if you don't like doing all these example numbers, then you're thinking like a mathematician. Here's a peek ahead to see the start of how the quote-unquote hard, proofy part of all this will go. Let's measure the positive distance from 0 to the edge of our slices by the variable delta. No worries, this is just a regular letter which happens to be Greek. The picture we see for the values of x in the first slice is written in words by an inequality, 0 less than x less than 0 plus delta. Similarly, the picture for values y in the second slice is represented by the inequality 0 less than y less than 0 plus delta. We want to know about the possible sums of all such values of x and y, which is just what variables are for. These inequalities happen to be easy to add. 0 less than x plus y less than 0 plus 2 delta, which we can see gives us a slice of 0 plus that's twice as wide as the summands were. This shows us exactly what a slice of the sum looks like with no example numbers whatsoever. Now back to the matter at hand. What happens when the summands squeeze? We keep the closer numbers, but lose more and more of the numbers that are farther away, causing numbers in the slices of the summands, and thus those in the sum, to squeeze closer and closer to 0. The result of this sum fits into 0 plus. It's twice as wide as the summands were, but it does hit every target that 0 plus paints. In fact, the sum is equivalent to 0 plus. We could use a double-headed arrow here, and in every other case we'll see for arithmetic, just as with our function results. But we still want to get in the habit of using the regular arrow. We'll see just why when we get to limit computations. This first simple example shows us how arithmetical operations work on near numbers. They act on all pairs of numbers, one from each slice, and the result squeezes with them. The rest of this video will highlight some of the finer points of these operations and work through some illuminating examples. Let's change the question just a bit. Let's add a dot to the first summand, making it 0 plus dot, so that it now contains the number 0 itself. The only change is that we can now get a sum where the first number is 0, but the second number will still always be positive, so our result is still 0 plus. What if we also add a dot to the second summand? Now, one of the sums we have is exactly 0 plus exactly 0, which gives a sum of exactly 0, and our result becomes 0 plus dot. This might seem like nitpicking, but think back to reciprocation. The reciprocal of 0 plus gave positive infinity. The reciprocal of 0 minus gave negative infinity, and the reciprocal of 0 itself is undefined. It can sometimes be critical that we pay attention not just to what number we're squeezing toward, but how we're squeezing toward it. Let's change this up a little bit to 0 plus 0 minus. We're still adding near numbers that squeeze towards 0, just as before, so the result should be squeezing towards 0. Let's see which adornment we need on that 0 to capture our result. Adding numbers toward the left of the slices, we have things like 0.1 plus negative 0.4 equals negative 0.3, and 0.01 plus negative 0.49 equals negative 0.48, which get arbitrarily close to negative 1/2. Adding numbers toward the right of the slices, we have things like 0.4 plus negative 0.1 equals 0.3, and 0.49 plus negative 0.01 equals 0.48, which get arbitrarily close to positive 1/2. As before, we can get any number in between as well, including 0 itself as 0.1 plus negative 0.1. The slice we get is the whole open interval from negative 1/2 to 1/2. When the summands squeeze, the situation is exactly the same but scaled down, and we see our result of 0 plus minus dot. Note that when adding 0 plus and 0 minus, the result expresses both of the adornments, as well as the dot in between. The fact that neither the plus nor the minus wins is exactly what we'll see later on when we get a peek at star forms for arithmetic. We've seen enough now to state the rule for addition of any basic finite near number squeezing towards 0, which is fairly simple. The sum will squeeze towards 0, so the rule is just for the adornment. If one of the summands is constant, the result's adornment matches that of the other one, and we're finished. If opposite plus-minus adornments occur between the two summands, the result gets a plus-minus dot, and we're finished. Otherwise, the result gets the plus or the minus the two summands agree on, with the dot if and only if both summands have dots. This is the full rule for adornments on sums of 0 something and 0 something. Of course, we could think through any example if we'd like. We don't have to simply memorize the rule. As for adding other basic finite near numbers, the good news is that addition of the bases works just like regular addition. For example, let's look at 1 minus plus 2 plus. The result will squeeze toward 1 plus 2, or 3. We have a minus in the first summand and a plus in the second, which disagree, giving us a result with plus minus dot. Let's take a look at that visually. Here are slices of the summands. Forming all possible sums, we get all of the numbers from 2.5 to 3.5. When the summands squeeze, the result also squeezes, showing us 3 plus minus dot. That's it for sums of basic finite near numbers. What happens if we add a basic finite near number to positive infinity? Suppose we add negative 1,000 plus minus dot to positive infinity. We plot both slices and see where the sums live. We're adding around negative 1,000 to each number in the slice of positive infinity. So the result is slid back around 1,000 units. Now what happens when they squeeze? The negative 1,000 plus minus dot just squeezes in towards negative 1,000, which doesn't have much effect on the sums. The positive infinity, on the other hand, pushes farther and farther to the right, which eventually has quite an effect. We see that our result fits back into positive infinity. Though it gets a late start, these sums eventually stay inside any target positive infinity paints. Neither our choice of the number negative 1,000 here, nor its adornment, is of any consequence. The same happens if we add any basic finite near number to any basic infinite near number. The infinite one eventually pushes far enough that the influence of the finite one is effectively lost in the sum. Finally, we get to the big ones. What happens when we add a basic infinite near number to another basic infinite near number? Adding positive infinity to positive infinity is no problem. Here are the slices of positive infinity. Adding all of the numbers in the first to all of the numbers in the second just ends up doubling the starting point. And when we squeeze, we see a result that very definitely fits into positive infinity. It goes similarly if we add negative infinity to negative infinity. Here are the slices of negative infinity. Adding all the numbers in the first to all the numbers in the second just ends up doubling the starting point again. And when we squeeze, we see a result that fits into negative infinity. Now what we've been waiting for. What happens if we add positive infinity to negative infinity? Here's a slice of positive infinity and one of negative infinity. Let's look very carefully at the sums we get. This might remind you of when we added 0 plus to 0 minus. We have arbitrarily large positive numbers added to, say, negative 2, giving large positive numbers, as large as we like. On the other hand, we have 2 added to arbitrarily large negative numbers, giving large negative numbers, again as large as we like. And in fact, we have any other number we like if we choose an appropriate pair of summands from the slices. Now what happens when these near numbers squeeze? Absolutely nothing. No matter how far they squeeze, we can do the same thing to get any positive or negative number we like. For example, right here, 2 is 1003 plus negative 1001. So the result fits into negative infinity infinity, the whole real line, which we also denote by star. This is the fundamental star form for addition. The same thing happens if we add any two basic infinite near numbers that give us a positive infinity and a negative infinity opposite each other in the sum. That is, positive infinity plus negative infinity in either order, and any sum of basic infinite near numbers with positive negative infinity. A note's in order here. The sum doesn't just fit into star. These near numbers are actually equivalent and they both diverge. So we're not seeing actual indeterminacy yet, which is why we prefer to stay star form. But if we were to say that a near number alpha fits into something like this, that statement will be indeterminate, because we wouldn't be able to determine whether alpha converges or not. Before we go, let's talk a bit about subtraction, which is simply addition of a negative. Negation can be understood geometrically as flipping the real line about 0, and there are easy rules for negating both basic infinite and basic finite near numbers. We negate the base and the adornment. So what's 3 plus minus 2 minus? We simply add the negative of 2 minus, which is negative 2 plus. We add the bases, and the adornments agree on plus, so our result is 1 plus. Any other difference can be similarly broken down as adding a negative. The star forms for subtraction come from those for addition. The basic one is positive infinity minus positive infinity, because this simply means positive infinity plus negative infinity, which we saw earlier. Let's review the details. Here are slices of the two positive infinities. Now what differences can we form as a number from the first slice minus one from the second? We can subtract 2 from arbitrarily large positive numbers, giving us arbitrarily large positive numbers. We can also subtract arbitrarily large positive numbers from 2, giving us arbitrarily large negative numbers. In fact, we can get any real number by choosing appropriate values from each slice. It doesn't matter how much this squeezes. The same analysis applies, and our result is always the same, the whole real line, or star. Similarly, the rest of the star forms for subtraction arise any time that we have a difference that includes infinities of matching sign opposite one another. Positive infinity minus positive infinity, negative infinity minus negative infinity, and any difference of basic infinite near numbers including positive negative infinity. With that, we close our introduction to addition and subtraction of near numbers. Our next video will continue with multiplication and division, then we'll talk more about indeterminacy and star forms. We'll finish this video series by discussing expressions and limits, then formal proofs. Please share this video and check our blog, where we'll announce new videos and discuss questions that come in. And don't hesitate to use the contact email below if you have any questions along the way.